Dynamic programming. Unraveling the art of efficient problem-solving. Dynamic programming is a powerful technique in computer science that optimizes problem-solving by breaking down complex problems into simpler overlapping subproblems. This approach allows programmers to store intermediate results, often called memoization, to avoid redundant computations and enhance efficiency. The essence of dynamic programming lies in identifying patterns within these subproblems and reusing previously computed solutions. It finds widespread applications in various domains such as optimization, graph theory, and bioinformatics. By mastering dynamic programming, developers can significantly reduce time complexity in many challenging scenarios. Understanding the core principles of dynamic programming. To fully grasp how dynamic programming works, it's essential to understand its two fundamental properties: optimal substructure and overlapping subproblems. Optimal substructure refers to the property where an optimal solution to a given problem contains within it optimal solutions to subproblems. Overlapping subproblems occur when the same subproblem needs to be solved repeatedly during the computation process. In contrast, non-overlapping problems are handled better through divide-and-conquer approaches like quicksort or merge sort. These principles form the foundation upon which all dynamic programming algorithms are built. Recognizing them helps identify situations where applying dynamic programming will yield significant performance improvements. For example, consider Fibonacci sequence calculations using recursion without any optimizations. The naive recursive implementation computes each value independently, leading to exponential time complexity due to repeated calculations of identical subproblems. Optimal substructure. A problem has optimal substructure if an optimal solution can be constructed from optimal solutions of its subproblems. Overlapping subproblems. When solving larger instances of a problem, smaller subproblems get reused multiple times, making caching beneficial. Design patterns for implementing dynamic programming. Implementing dynamic programming effectively often involves choosing between top-down and bottom-up strategies based on specific requirements and constraints. Top-down methods employ recursion alongside memoization to cache already calculated values, while bottom-up techniques build up solutions iteratively from base cases upwards. Each strategy offers distinct advantages depending on factors such as memory limitations or expected input sizes. For instance, top-down implementations may lead to stack overflow errors under deep recursion conditions but allow for easy modification of parameters mid-calculation. Memoization plays a crucial role in both paradigms. By storing intermediary results either globally via tables or locally within function scopes, we prevent redundant computations across different branches of our algorithm execution tree. Selecting appropriate data structures for storage also affects overall performance characteristics significantly. Hash maps provide fast lookup times at the cost of increased space usage, whereas arrays offer direct indexing access with predictable size allocations. Time complexity analysis. In dynamic programming, evaluating time complexity becomes critical when comparing different algorithmic approaches aimed towards solving similar problems efficiently. While brute force solutions might run in O(2 to the power of n) time complexity for certain tasks like calculating Fibonacci numbers recursively, optimized versions using DP could bring those figures down dramatically. A common pattern seen across many successful DP implementations includes reducing exponential running times into polynomial ones. The key here lies not only in recognizing overlapping subproblems but also structuring your recurrence relations correctly so they align well with available resources. Let's take the classic longest common subsequence (LCS) problem as case study. Its standard recursive formulation yields O(2 m plus n) runtime, whereas implementing it with a table-based method reduces complexity substantially, downwards toward roughly O(m n), where m and n represent lengths involved in comparison operations respectively. This reduction demonstrates clearly why understanding how different choices affect final asymptotic bounds matters greatly when designing efficient software systems today. Space optimization techniques in dynamic programming while reducing time complexity remains paramount, Minimizing space consumption is equally vital, especially when dealing with large inputs or limited hardware capabilities. There exist several advanced techniques aimed specifically at achieving this balance between speed and resource utilization. One popular approach known as space compression focuses on limiting array dimensions used for tracking state transitions instead of maintaining full matrices throughout entire calculation phases. This technique drastically cuts memory footprints without sacrificing correctness guarantees provided by traditional DP frameworks. Another notable trick involves utilizing single-row or even constant space variables whenever possible. In some instances, particularly when only immediate prior states influence current decisions, we needn't retain historical records beyond what's strictly necessary. Consider the matrix chain multiplication example, which traditionally requires n cubed time along with theta n superscript 2 auxiliary memory allocation. Through clever rearrangement of loops combined with selective retention mechanisms, it's feasible to implement variants requiring less than half original disk footprint yet preserving identical mathematical rigor. Applications across industries where dynamic programming shines. Dynamic programming extends far beyond theoretical discussions. It powers real-world innovations impacting diverse industries ranging from finance to genetics research. One prominent application area relates closely to financial modeling involving stock price prediction and risk management simulations. In computational biology, scientists leverage dynamic programming algorithms extensively for DNA sequencing projects aimed at uncovering hidden genetic traits among populations. These models help compare vast genomic datasets efficiently despite their sheer volume complexities. Furthermore, video game development companies frequently apply DP techniques during pathfinding optimizations inside AI behaviors, ensuring characters navigate maze-like environments realistically without excessive lag issues affecting gameplay experiences negatively. Even supply chain logistics benefit immensely from adopting these methodologies, allowing organizations plan inventory levels accurately considering fluctuating demands dynamically over time frames spanning weeks/months ahead. Common challenges faced during implementation phase. Despite numerous benefits associated with employing dynamic programming practices, practitioners commonly encounter hurdles preventing seamless adoption, particularly amongst novices unfamiliar with core abstraction layers required beforehand. An initial challenge stems from properly defining recurrence relationships, accurately capturing desired behavior. Mischaracterizations here result ultimately flawed outputs regardless how meticulously other steps executed afterward. Additionally, debugging becomes exponentially harder compared conventional sequential programs because changes propagate unpredictably through interconnected cells, forming multidimensional grids representing varying states throughout iterative processes. Sometimes premature commitment made towards particular solution formats restricts possibilities, exploring alternative pathways, possibly offering superior trade-offs concerning accuracy versus execution durations metrics. Tips and tricks to master dynamic programming concepts. Building proficiency necessitates consistent practice coupled strategic learning approaches emphasizing foundational knowledge rather mere memorization tricks alone. Engaging actively hands-on coding sessions proves instrumental, reinforcing conceptual clarity, practically applicable contexts. Start experimenting gradually, starting simple problems, progressing increasingly intricate ones once comfort levels elevate sufficiently. Identifying recurring themes underlying multitude seemingly unrelated puzzles unveils broader perspective regarding universal design principles guiding effective algorithm construction. Utilize visual aids assisting comprehension, such flowcharts mapping out decision trees illustrating stepwise progression through iterations, helping pinpoint precisely where logic diverges unexpectedly away intended outcomes. Seek collaboration opportunities, participating online communities, dedicated focused groups exchanging ideas, troubleshooting difficulties encountered regularly, faced experienced peers providing insights otherwise hard accessible solely. Independent efforts. Future trends and innovations around dynamic programming paradigm. Emerging technologies continuously reshape landscape, influencing evolution direction taken. Future developments centered around dynamic programming concepts itself. quantum computing promises disruptive change, potentially rendering classical approaches obsolete overnight, though exact implications remain speculative pending further advancements. Machine learning integration opens exciting avenues, enhancing predictive analytics capacities previously unimaginable, leveraging hybrid architectures combining neural networks alongside traditional DP frameworks, delivering unprecedented precision rates achievable before now. Cloud computing platforms facilitate distributed processing environments, enabling parallelization of formerly sequential operations, improving scalability aspects, significantly reducing latency concerns prevalent earlier stages. Technological maturity curves. Blockchain technology introduces novel security paradigms demanding adaptive responses, including redesigns existing protocols, ensuring robustness against emerging threats, exploiting weaknesses, inherent legacy designs, vulnerable cyber attacks, targeting decentralized infrastructures, rapidly growing popularity nowadays. Conclusion: dynamic programming stands out as cornerstone methodology empowering modern software engineers tackle computationally intensive challenges, gracefully balancing trade-offs between performance gains versus resource expenditures, prudently managed simultaneously. By internalizing its nuances, thoroughly equipped professionals wield tremendous power, transforming abstract mathematical constructs concrete working implementations capable tackling complex industrial-scale problems confidently today, tomorrow alike.